Welcome. We're going to take a look at multivariate normal distributions. We've seen in the multivariate regressions that, in multiple regressions, that we end up with correlated random variables, which are linear combinations of normals. And we're going to look at what the probability distribution is for these. And for that, we need to develop a couple of tools. So first of all, you'll remember the ordinary standard normal distribution. If this is the density, it's 1 over root 2 pi e to the minus z squared over 2 for all real valued z's. Or if you have a bunch of these z's, then each one of them will have a density of this form. And you need to distinguish between the different variables. So the density of zi, capital Zi, is this quantity. Now, if they're independent, then the joint density, by definition, is the product of the individual densities. So you multiply them all together, and you get this quantity. And then, so this is the easy case, the independent case. And now what we're going to do is we're going to look at linear combinations. So suppose we have a matrix, n by n matrix, and a mu in Rn, and we define a new variable, random variable, to be this projection of A plus the mean. Then, of course, you'll remember that the expected value of y is equal to the expected value of AZ. Expected value of Z is 0 for all the components. So this is just mu. And the variance covariance matrix of y is going to be A times A prime, A transpose, because the variance covariance matrix of Z is just the identity matrix, because each one of them is almost 0, 1, and they're independent. So we know the mean and the variance, but we haven't developed the actual distribution. And to find that, we need to go to multivariate calculus and go to a theorem which has to do with variable substitution. And it basically says that if you have a one-to-one function where with a derivative, so that the derivative of g with respect to y is going to be a matrix. So this is, remember, this is an n-dimensional transformation. So you can differentiate each of the components of g with respect to each of the y's, and you get a matrix. The Jacobian determinant is this quantity here. This star is supposed to be here. And this determinant is just a number for any given value of y. It's a function of y. And you think of this as the derivative of the z's with respect to the y's. Now you'll notice that this g is the inverse function of what we had before. So g of y in our case is a inverse times y minus mu, like this, more or less. And for our special case. But in general, this holds under appropriate minor assumptions on differentiability and so forth. And so this will typically be an integral over some sets. There may be a set, let's see now, B for y here. So if this is an integral over set B, then this has to be the corresponding set on the left-hand side for when y is in B, Z is in some other set. And so let's look at this. This left-hand side here, if this is an integral over some set A, and I'm sorry about the double notation here, then this will be the probability that C is in the set A. This vector random variable C is in A. Now we know that A is a function of that C is a function of y, and C is just G of y. So this is then the probability that y is in the corresponding other set. So if C is in A, then G of C is in G of A, and then y is in B. So this is the probability that y is in the set B. Okay, now that's interesting. So what does this say now? This says that the probability that y is in a set B is equal to integral over B of a certain function of y. But this is exactly the definition of a probability density function. A probability density function is a function such that the integral of that function over the set is equal to the probability of the random variable being in that set. So we're done. This is now the density of y. This quantity here is the density of y. So for this general transformation, this is the density, and now we just need to solve with a little bit of linear algebra, figure out what this is. We need to go, in other words, from this quantity, figure out the Jacobian. The Jacobian is just the matrix, and then convert the two. And we then find that the density of y is equal to this quantity. And you'll notice what happens here. This sigma matrix, there's a determinant of it, and the determinant of and sigma here is A times A transpose. That's because we're getting these variances coming in. So the determinant of sigma is just the determinant of A squared. Here we get, basically we have A transpose inverse, and if we call that A transpose sigma, then this is sigma inverse. And so this is the variance covariance matrix of the y's, which we saw earlier, and that variance covariance matrix comes in here. So this is the general formula for any linear transformation, for a distribution of any linear transformation of standard normal random variables. And but we did put one condition on it. We said A had to be invertible. And you see what happens if it's not invertible. This determinant is 0, and then we cannot compute this density. And that's not really a particularly interesting case. You should also note that if you take any x and take that times sigma times x, x prime, sorry, any vector, then this is x a prime x. So this is equal to it's ax a prime x prime times a x. There we go. Anyway, this is the point is that this should be the, doing something silly here, the norm of ax or a prime x. Yeah, there we go, squared. And this number is always greater than or equal to 0. It's only 0 if a prime x is 0, but a is not singular. So this is equal to 0 only if x is 0. This is greater than 0 if x is not equal to 0. So what this means is that sigma is positive definite. So we only have the multivariate normal distribution in the cases where sigma is positive definite. We may discuss later what happens if it's not, but it's not really interesting. So this is enough for everything we do.